and this is on Hall-Littlewood-Schubert affine Schubert series and lattice enumeration. And my name is Christopher Voll, and this is joint work with Joshua Maglione. He featured now on 3 talks, so he's one of the 5 guys. Yeah. I'm not, I'm another guy. Yeah, and I'm thrilled to be here and honored to be able to address you. Thank you very much for having me. Actually, thanks are due to thrice. Thanks for having me this week. Thanks for having me in 2018. I remember I was here for 2 weeks and then I had to go back and teach. So I was back in Bielefeld and half of my group was here, so certainly the better half. And I thank you for keeping them entertained here. And it's great to see what happened for all of these 3 guys, I can say this. Anyway, logic and algorithms in group theory, I think is the title of this program. And sorry? Thank you. Algorithms in group theory, and I will try and use my remaining 9 minutes to convince you that at least there are some links between my work and this program. So in my line of work, we often start with an algebraic structure, most likely or not a group, G, and a prime number P. And with this data, we collect, with this input, we collect data about the group G. So we maybe have reasons to collect data, integers, 1 for each power of the prime P associated with this group. This way we get a sequence. So this could be, for example, be the number of index P to the n subgroups of G. Or Tobias told us about graphical groups. It could be the number of conjugacy classes of the Z mod P to the n points of a graphical group scheme associated with a graph, or something or other. And then, as Tobias showed us, more often than not, it makes sense to encode this data into a generating function, or for some reason, some good reasons, sometimes called zeta function. So what did Tobias do? He took these numbers he was interested in and took them as coefficients of a ordinary generating function. And this ordinary generating function could have as a variable this expression p to the minus. Yeah, but as it's written, it's just a power series. And now logic in the past has more often than not come in to tell us that these power series are not just any old power series, they are actual very nice functions, namely they are rational functions. So a meter theorem, which often kind of, at least in the first generation, comes from logic, tells us that for the right kind of primes, for the right kind of groups, the right kind of counting problems, these zeta functions are rational functions. Rational in p to the minus n. So in other words, this infinite amount of data is really given by a finite amount of data, namely a numerator polynomial and a denominator polynomial. And then naive-minded people like me are challenged to actually compute these things. Yeah? So often the model theory tells us it's rational, but it gives us no inkling whatsoever what these rational functions be. What is the degree of the numerator? What's the degree of the denominator? What are the zeros? What are the poles? Are there any reciprocities, special values? All of these things we are told by our colleagues from geometry and number theory to care about, but the at least first generation model theoretic proofs of these results very rarely tell us anything about this. So algorithms have been devised by a number of people, and Tobias Rossmann is surely the most prominent among them in this area of enumerative algebra that I'm active in, that then produce more or less explicit formulae for these rational functions. Tobias showed us, again, on one of the central slides in his talk, how these look like. So this, these rational functions explicitly as quotients of numerators and denominators allows us now to ask the kind of questions that I indicated to be interesting in geometry and number theory. Special values, poles, zeros, functional equations. Zooming into what this project with Josh is about, I would like to, appropriate for a very short talk, invite you to take pleasure in the simple things of life. I promise you there is a joy to be gotten out of abelian groups. So for the remainder of my talk, G will be Z to the n, just the free abelian group, rank n, and P is a prime. Yeah, I didn't tell you which prime. I mean, in a way it doesn't matter. I mean, sometimes there's a natural prime. For example, if this group G is a pro-P group, a virtual pro-P group. Or maybe it doesn't matter because this group G is arithmetic and knowing properties about it is equivalent to knowing properties about them for all P power substructures. Anyhow, if G is Z to the n, no prime is singled out, so any prime. And I would like to invite you to care about subgroups of Z to the n. So if I have a subgroup of Z to the n, I always think of this as a finite index subgroups, and I always, when I write this P, I mean it should be a P power index subgroup. There are two invariants that we teach our first years, maybe second years, about that we can pick up about this group. The first invariant is the type of the quotient. Yeah? So Z to the n modulo lambda is a finite abelian group, and as such given by a partition here, which picks up the elementary divisors, if you wish, of this group lambda, or rather the quotient. So in this way, I associated with this subgroup a partition lambda. Lambda is a partition of at most n parts, and that's an intrinsic invariant. Less intrinsic is another invariant that we also teach our first or second years. If you've chosen a basis for Z to the n as a module, you can represent your lattice lambda by a matrix recording generators. And if you do this in the right way, you can assure that this matrix is an upper triangular matrix, and you can even ensure that the diagonal entries are p powers. Yeah? B to the delta 1, right times B to the delta n, and then there's condition, some condition. So this is a matrix called in mean normal form. And in this way I've told you a second, well in this case composition rather than partition, associated with this lattice. And I would say it's an ambitious but certainly undergraduate exercise to enumerate all lattices in Z to the n according to one or the other of these invariants. And what Josh and I struggled for a long time with and finally solved, among other problems with the methodology in this paper, is how to do this simultaneously. So what we want to do is we want to solve the problem of writing down the generating function that runs over all finite index p power subgroups of Z to the n, and for each of these lattices record both the Smith normal form partition and the Hermite composition. So let me write a formal power series x to the lambda of lambda, where lambda is this partition associated with this way, and x is a vector of variables. And likewise, we have a monomial in some extra determinants y to the delta of lambda. Yeah, so for every lattice lambda, I have two invariants that I want to take care of, and I do this by viewing them as exponents of some monomials, and then I just run over all of these things. Now this is a rational function, it turns out, and what I really want to show you is that this is a rational function that is really an instance of a class of rational functions that maybe deserves attention from many different angles. And these are the so-called Hall-Littlewood-Schubert series. Let me ever so briefly tell you what Hall-Littlewood-Schubert series are. there was a long discussion which people's names should come into the definition here. And maybe you see some of the reason why we went for Hall-Littlewood and Schubert. So the Hall-Littlewood-Schubert series of degree n is a variable, is a rational function in many variables. We have 2 to the n variables. 2 to the n is 2 to the n minus 1 plus 1. 1 plays the role of keeping track of which prime we have here. Turns out that this question here depends on the prime in a uniform way. Uniformity in the sense that Tobias introduced before the break. But the main bulk of keeping track of the complexity of these two partitions is done by variables that are we think of as keeping track of the labels of the set of a semistandard Young tableau. A semistandard Young tableau is a standard tool from algebraic combinatorics. A semistandard Young tableau is just a way to put in numbers in a Young diagram in a certain way. That's one, for example. So that's a semi-standard Young tableau on labels 1, 2, 3. And it is reduced because no two columns are the same. So the Hall-Littlewood-Schubert series we get by running over all reduced semi-standard Young tableau. And we have a polynomial that is really a close relative of the Hall-Littlewood polynomial associated to these things that decorates here a product of geometric progressions, one for each column of the semi-standard Young tableau. I don't want you to get too much carried away with the details of what I said. I want to invite you to take in. This is an infinite series which has here a finite description in terms of something very classical, namely the finite set of semi-standard Young tableau on labels 1 to n without repeated columns. Now, this paper contains a number of theorems, and most of the theorems say you take a counting problem about lattices, and the statement is, well, this counting problem is solved by taking HLS and doing the right substitutions. So, one theorem is that this function that enumerates lattices both by Hermite and Smith parameters is an instance of HLS. Is an instance of HLS. Meaning there is a specific substitution of the variables that lets you get from here to here. And that's how I finish. Thank you.